Hi, everyone. Welcome to the talk on SFrame. My name is Indu. I work in the Linux toolchain team at Oracle. It's a pleasure to be here. Thank you for having me. How many of you have heard about SFrame before? Okay. Thank you. So SFrame was first released early 2023, and of course, a lot has happened between then and now. Things big and small, but I'll not talk so many things. I'll not cover many of the things that have been done till now. I'll focus on where we are at now and looking ahead. What are the things that we are looking at? And as I go through, I will try to pull in some of the specifics about what the format is all about. So hopefully you'll still get an idea about what the format is about and what are the problems that we are trying to address. So speaking on that, why SFrame, right? So since some of you have not heard about SFrame, I'll go over this stuff, but still spend some time on it. So basically, I call this like if you have heard of SFrame, you have also heard about, generalized org for user space. Some people say that, SFrame is like generalized org for user space, and which is true. So both SFrame and org try to address this unattended gap between the existing recipes for stack tracing. So on one hand, you have frame pointers. We know what it is. It's a simple method. You use a register to sort of traverse what is a linked list on stack. And it's a simple method. The compiler sort of does some work for you. But as you see, this method is at odds with the compiler. The compiler wants to aggressively optimize, and it does not like to preserve this register because it meddles with its goal of optimizing the code, especially on some architectures, right? So soon you realize that fno omit frame pointer. So you ask the compiler to not omit frame pointer, and over time you realize, okay, this is not the silver bullet. I do need to worry about, say, leaf functions too. So frame pointer is at odds with what works for an optimizing compiler. And the bigger problem with frame pointers is that back of the envelope calculations have shown that 5 to 7% of your stack traces are going to be imprecise. You will miss frames when you're trying to stack trace from those few instructions where you're still in the process of setting up the frame pointer, right? So on one hand, we have frame pointers. It's simple, but there are reliability issues with it. And on the other hand, as EHFrame, well-known, solution, very powerful, extremely reliable, the most reliable, in fact, to get your stack traces. But the problem with EHFrame, as we know of, is that the stack tracer implementation gets bulky. And this is one of the reasons why it's not suitable to be used in environments where, basically resource-constrained environments, you are limited with how much you can do when you are stack tracing. And so there are requirements that you want to use something leaner, and which is where SFrame comes into picture. It was designed to bridge this gap. And basically, SFrame is it's a subset of the information that EHFrame gives you, and then SFrame is all about simplifying that information as your next step. So that's how it brings you the reliability of EHFrame, and it reduces the complexity, stack tracer implementation complexity. Now, the last point here is asynchronous stack tracing, and by that what I mean is the overall coverage of the format, right? You do want the capability to stack trace from each PC in your program. So SFrame is quite close to EHFrame. There are few patterns that we know that are not supported, which basically means that there will be few of these functions where there will be no SFrame information for you. But the coverage is quite high, and it should work in most of the cases. And going back to the whole why of this project and everything, when we started with this project, and we had this question, okay, why not explore something which is EHFrame-like, but still addresses these problems. And I know many of you also have had that question as well. So I'll try to answer that. So to answer that, let's look at what EHFrame is for, right? EHFrame is for stack unwinding. Stack unwinding is a process in which you go from a place in your program to a previous point in execution. You want to restore some state of the program, which is basically CFA registers and callee saved registers, and possibly also rolling back some program state, but that's beside the point. As far as EHFrame goes, you want to restore some number of entities. What is the number of those entities? There are these CFAs and callee saved registers that you would want to restore. Now, because this is too much information, EHFrame does compaction. It has a style of compacting this information, which is to say that EHFrame says, I'm going to give you some opcodes. Execute these opcodes. If you're the stack tracer, execute these opcodes and get your stack offsets and do stack tracing. So you see there is a program basically that you need to execute to do stack tracing. And that's where most of the complexity in stack tracers also comes from. So the first piece of complexity that comes from using EHFrame-based stack tracer is this whole concept of executing dwarf opcodes and implementing a small sort of decoder or a virtual machine to execute these opcodes. And the same mindset also shows in how EHFrame makes choices about encodings, right? There is LEB encodings which are highly compact. They favor compactness over simplicity in encoding and decoding. So it makes sense, right? If I were to tell you that SFrame, for stack tracing, your need is not to restore all registers, but just few of those entities, it makes sense to simplify with that as your goal. So if there are only 3 of these entities that you have to track, is it worth it to then go with the same principle that let me compact this information as much as I can, execute these opcodes, use these encodings, de-encode at the time that you're stack tracing, and then do your stack tracing. If there is limited set of entities that you're tracking, SFrame comes in with saying, there is a faster way to do it, and because the information is so limited, let's try to do stack offsets directly. So hopefully that answers the question. Let's not get into the other aspects. I think that will be too much of a detail. And so I have some slides that talk about how the information is laid out. SFrame information layout is quite simple. There are few basic things. The SFrame header is like 20 or so bytes of information about some like flags or what is the endiness of this format, usual things. Then there is an entity called SFrame function descriptor entries. So this is an output that you can see if you use binutils and say use objdump minus gsframe or readelf minus gsframe, you'll see this output. And so this is the function metadata. It tells you what is the start PC of this function, what is the size, and so on. This is stored in what we call, as SFrame terminology, we call it function descriptor entry. So these function descriptor entries are fixed size entities that are stored in a stub, in a basically subsection in this area in SFrame. And these are fixed length entries. They are started on the start PC. And the bulk of the stack trace, the meat of the stack trace information where you store, say, the specific offsets that you need to use, they are called the frame row entries, and they are all stored here. So basically, I'm trying to introduce some keywords to you, which I will use throughout the presentation. So remember, function descriptor entry, it's just the function metadata. Frame row entries, it's the meat of the stack trace information where you store stack offsets. By stack offsets, I mean these entries here. So this says for this particular PC, the CFA is going to be SP plus 16 bytes. Okay, so in SFrame, if you use binutils, you can generate SFrame sections by using the assembler and passing it a flag minus gsframe. SFrame section, the current way we use it is that the section is named .sframe, and the current version of the format is v2. In your binaries, in your executables, and also shared libraries, you will see SFrame section appear in read-only ptload segment, and there is an additional program header that you will see, and the only purpose of this program header is to in turn point to where in memory this SFrame is loaded, and this just helps stack tracers to quickly get access to where the SFrame lies. Let's skip these two for now. It was just to say how to quickly access SFrame information, but the first step is how does it come in your binaries? It comes in as an F section. There is a program header type that you access to get the SFrame data. Few more things on where we are at in general with SFrame. So summary till now, SFrame is a stack tracing format which you can use if you do not want to preserve frame pointer, and if you have the use case where each frame is getting too bulky for you to be used for stack tracing. SFrame stores the stack offsets directly. So the first version that we released was 240 version 1. It is now obsolete. We added support for 2 architectures to begin with. I think the thinking there was, you always find interesting things when you add the second architecture. Let's not do something which is too tied to one ABI. So that worked out well, actually, in hindsight. Fast forward, 245 was recently released, and we have done some. So most of the things that we have done so far are bug fixes, feature additions. We added support for S390. I will talk about it. So by the way, whenever I don't know if you guys see the color difference, but whenever it's green, I will talk about that in the next few slides. 246 is when we are planning to release SFrame v3. I would like to talk about that too. But that's all I have got to say for now for SFrame. If you want to follow up on your own time, there are a few of these links that you can go through. Okay, so where are we now? As I said earlier, it's been in development for a few years now, and it's been an exciting time overall. Now, especially for SFrame, there are so many of these puzzle pieces that all of us as a community are trying to get together, get them to fit well. On one hand, we have the toolchain support. On the GNU side, we have been working on quite actively on making this a robust solution, adding more features, more architecture support. LLVM has recently started to add SFrame support as well. Gentoo and Ubuntu have helped us quite a bit by testing, by doing a distro-wide testing with SFrames enabled. Some bugs were seen, we fixed those. The other 2 components are also quite interesting. I will talk about those 2 in details. Kernel space stack tracer and user space stack tracer. On user space, we have 2 ways in which users will ask stack tracing. One is glibc backtrace function, and the other is the kernel's user space stack tracer itself. On the kernel space stack tracer, there is a use case being explored, which is the live patching on ARM64 using SFrame, because SFrame gives you that option of getting reliable stack traces. Okay, so toolchain support, I thought it will be interesting to just go over some of these items. This is not an exhaustive list, but still might be interesting to share. So we recently added support for S390X. S390X is, when patches first showed up, it looked like S390 is a flexible ABI. And I say flexible completely in context of SFrame, by which I mean that SFrame really likes simplicity. It really likes those ABIs where the semantics are clear in the sense that if the return register, if there is a return address, obviously it better be in one register, or if it's not in that specific register, it's saved onto stack, similar with frame pointer. So it really likes that sort of simplicity. S390 shows up. S390 is a flexible ABI where what it does is there are leaf functions where you will see that the return address is in a floating point register, for example. And initially we had those sort of tension between what S390 is as an ABI versus what SFrame can do. Over time, as I'll speak in the next slide, we did figure out some solutions, and the light at the end of the tunnel was because we addressed it from the starting, to work for 2 ABIs. So this is the solution that we used for fixing that problem. So basically, so now recall when I was saying there is this SFrame FRE block of there is this part in the section where all the FREs are sort of stored together. Those offsets, they are basically stored as blobs of data, and it is left, SFrame leaves it to the ABIs to define how do you want to interpret that blob of data. On x86, the SFrame specification says, for x86, the blob of data needs to be read as, first offset is a CFA offset, and the second offset, if present, will be your FP. For AR64, the rules are different, but specific to AR64, right? So for AR64, it says the blob of data, the first offset is going to be CFA. The second and third, when present, will be these in order. So S390, we could define ABI-specific rules, and we said, fine. For S390, if the last bit is set to 1, this means that this is not an offset, but a register itself. And this worked well for S390. Now remember, this is only for topmost functions. So which means that even if the stack tracer sees that the return address is in a register, it is fine because the topmost frame has access to all registers. You're not yet saying, SFrame will never be able to tell you how to restore all the registers. SFrame only gives you information for those 2 or 3 specific things. So, and over time, I think another thing that we also realized was interesting, and it's maybe useful to share, is that it goes a long way to make some provisions in your ABI. If you so desire to have fast stack tracing, it makes sense to make provisions in the ABI towards that end. So in S390, we did go ahead and specify that fine print, which is to say that there is a frame pointer, there is a register with a designated role of frame pointer. If at all there is a need to use frame pointer, this register be used. And it worked out well in the end for S390. We do have, working binaries, stack tracing works well. There are other interesting things that showed up with some of the usages that we did of SFrame on ARM64. Probably some of you guys might remember how painful this was, but this was a bug that we found when kernel modules were being compiled with SFrame. So the relocatable links were completely broken, and it was a nightmare of a bug, but whatever, it's passed behind us. Basically, the GNU assembler and the linker were doing 2 different things. We resolved it eventually, so 245 binutils is where you'll see the fixes to it. Basically, the fix there is we had to introduce an errata version of the format. Now, SFrame doesn't have minor versioning, so there will always be errata versions as and when necessary. Other key highlights so by the way, I'm going over what are the key highlights, right, for each of those 4 components and where we are at now, right? So the second key highlight from the component of where we are, how is it evolving? We are planning to do SFrame v3, and we have been keeping a list of what are the, feature requests that have come up so far, and we plan to target binutils 246, which is scheduled to be released late this year. The other thing that might be of interest is the option of enable default SFrame, which is an option for distros to enable SFrame distribution-wide, right? So far, Gentoo and Fedora have shown interest, and as this evolves, we would expect more user space. We would expect more usage of SFrame and user space binaries. Now, other key highlights on the user space stack tracing side, as I was mentioning, we added support for backtrace in the backtrace function in glibc. Support for SFrame has been added, which basically means that, and it's been released in glibc 242. It was released as an experimental version because it was too close to the binutils release, and ideally we would have liked to test it a bit more, but it should work for all cases. So if you build glibc with enable SFrame, glibc will enable the code where now where the backtrace function, if it sees SFrame, it will use SFrame data to backtrace. If it doesn't see SFrame, it falls back on dwarf. So that has been implemented. It can be tried with binutils 245. So if you generate your binaries with 245, binutils 245, and use glibc, you should see some SFrame action. And the other exciting pieces are, of course, this other stack tracers. So user space stack tracing in Linux kernel is also being worked on. Steve, Josh, and sorry if I'm forgetting more, Namyoung have worked on much of these patches, and Steve is here for any questions and follow-ups. But deferred stack tracing infrastructure has been put in place. Basically, on the kernel side, for user space, right? If you are using SFrame, there can be a page fault. You're accessing user space memory. There can be a page fault. Page faults are not is not something you can do in especially in NMI context or certain other contexts. So there was a deferred infrastructure. There's a deferred infrastructure thing in place now where basically the kernel puts the task of stack tracing, defers the task of stack tracing, and at the time when you're switching back to user space, you take up that work and stack tracing is done at that point. Of course, there's work involved there in the sense that you will need to now weave that initial request of stack trace to the point when the stack trace was actually given to you, and also doing the work of weaving this user space stack trace with the kernel space stack trace at that specific point in time. On the kernel space stack tracing side, of course, there's an effort for using SFrame stack traces for reliable live patching, reliable stack traces for live patching. I will not talk about those in detail either for now. So where are we headed? I think we expect more of all of this, to happen. On the SFrame v3 side, we are planning to do a few more of these feature additions which are important to ensure robustness of SFrame format. I will talk about each of these in detail. So there is more to the list, but I will not go over many of those items. If you're interested, then please take a look at the wiki page. These are mostly the list of items that we have created over time using, some patch reviews, some user requests, or just some self-research, actually, in some cases. But the first is supporting text greater than 2 GIB. So currently, if you feed linker some input objects and the overall text is greater than 2 GIB, then the linker will complain. The linker will say, this offset is too big for me. This is out of range for me, this particular relocation. This, by the way, is also a problem with EHFrame. And since nobody has ever reported this problem, this likely is not a real problem out there. But moving forward, this can be a problem, so better address, at least for SFrame now. So what is the problem? So going back to that whole thing about representation, right? Recall that representation when I said there are function descriptor entries. So what does the function descriptor entry actually look like? It's actually just 28 bytes of data. The first entity is the function start PC offset. So this basically says what is the offset of the function? What is the data for the offset of the function from here until where the function actually lies in the text? So right. So since this is 32 bits, of course the problem is because this is 32 bits. And what is the solution? The solution is to increase this to 64, but then we don't want to bloat the format so much. This itself, if you just simply move to 64 bits, you will see 6 to 7% size of increase in SFrame sections. So of course the padding can be removed. This was initially added for just alignment reasons. And you could reduce the number of the size of this member here, which says number of FREs, because over time we realize that this is not something that needs 32 bits. 16 bits will be just fine enough. So by the way, this method of storing offset here, which is the offset from this field to the start PC in text section, it's pretty common. Each frame does it, and this is the way you would store in any binary, because you don't want to pay the cost of relocating these sections every time you load to a new memory location, right? So that's about it. The first problem is supporting text for greater than 2 GIB. There is a solution in place. I think we should have this in binutils 246 when this is released. Let's skip over these. Let's not get distracted, but I'll come back to these maybe a bit later. Outermost frames. So so far in SFrame, there is no way to encode the outermost frame explicitly. There is no way to, if you're the stack tracer, there is no way to tell that this is the outermost frame. It just didn't exist till now. But over time, we are realizing that it is useful for the stack tracer to be able to determine that this is the end of stack trace versus coming to a point and saying there is no SFrame, right? So stack tracer goes ahead and does backtracing. At some point, it sees no further SFrame. It doesn't know whether the case of no further SFrame is because some application wasn't just compiled with SFrame, or this is really the start of the outermost frame. So to disambiguate between those cases, it will be good to add that. And Dwarf has it, by the way. Dwarf has this DW CFA undefined, and we are planning to put that in SFrame too. The way we will encode it is that you will see an FRE with no offsets. So then the stack tracer will be able to tell unambiguously that there is no, that this is the outermost frame. The last is unaligned accesses that I can talk about a little bit. Although over time we realize that this is not something we want to address, but maybe it's worth sharing. So going back to that whole layout thing that we talked about. So this is the layout of the SFrame section. The SFrame header, you always have aligned accesses. SFrame function descriptor entries, again, always aligned accesses. It is in the specification that SFrame header and SFrame function descriptor entries are aligned accesses. But for SFrame row entries where you're storing these offsets, this may cause unaligned accesses. And the reason is that you favor compaction in your encodings. You want to put this data could be just 1 byte, 2 byte, or 4 bytes. You don't want to space the space in padding. You want to put this data as close as possible so as to save space. So again, zooming in further, where are the unaligned accesses coming from? So each FDE points to the first FRE of a function. So it points to where the meat of the stack trace information lies. And that meat of the stack trace data is basically the start PC, some information about how to interpret this varlen set of data. This varlen set of data is basically all those stack offsets. This is the place where stack offsets are stored, right? So where do the unaligned accesses come from? They'll come from PC offset from start function and varlen data. So what is PC offset from? So suppose you have a function of, say, 80 bytes. You want to store so the maximum that you will have to encode is 80 bytes of information. So you just need 1 byte, which is sufficient for encoding this PC offset from function start, right? So, but this is chosen per function. There may be functions which are larger than 255. 256. So then you will use something like 16 bits of information. So this is chosen per function. Again, choice per function, storing things as close to each other is where the compaction is designed into the format. And this is also where unaligned accesses come into picture. But what is the problem with unaligned accesses? The only rationale to avoid unaligned accesses is for performance, right? But on newer architectures, that's less of an argument, one. But there may be, the other argument was, well, maybe in future you may want to support SFrame on architectures which do not allow unaligned accesses. What do you do then? Again, there are solutions that you can use there, but we wanted to see if there is if now is the time to take a step back and just address this problem, and if there is a better solution to the problem, right? So now we know where the unaligned accesses are coming from, and we wanted to see if there is a way to solve them. There were some things that we explored. You could restructure the data. So maybe I don't want to get into too many details. They may not be necessary. But basically, you could restructure the data. So store. Okay, sorry. You could store the data differently. Like you could bucket them. You could bucket them in store all 8 bits together, store all 16 bits together, and so on. But it just complicates the way you access data, right? And there were other solutions where we said, okay, let's put some index then. If there is problem in accessing data, put a reverse index or something. But then it bloats up the data, bloats up the format. So all in all, we considered some solutions, but it is not worthwhile to give up on compactness just for performance, especially in this case, you're talking about performance for unaligned accesses. So in this case, the argument has been, I think, mostly settled that we will not address this. There will be unaligned accesses in the format. And if at all there are cases where you cannot do unaligned accesses, use memcopy. And this should not be too high a number. This should be only, O. So for example, if you have, this should be of the order of the number of frames that you have, plus some constant. It shouldn't be too high. Okay, so far we've talked about SFrame as a simple frame stack trace format. There are, as you see from what I've spoken today, there are iterations that we are doing as we proceed forward to make sure that SFrame fits into this role of user space stack tracing, this role of doing this user space stack tracing well and efficiently. And there is active community involvement in so many multiple pieces. We're looking forward to things converging soon, and distros enabling SFrame so that we can have fast, reliable stack tracing. And that's all I had for today. Thank you.
One small question. Would it be completely out of scope to optionally add additional information on each function definition block, like the file name, the symbol name, or stuff that could be helped while executing the stack trace to display more, let's say, direct information on the symbol and the function we are dealing with?
Yeah, I mean, typically we like to keep symbolization aspect out of the stack trace format itself. I do realize that, so there are ways to solve symbolization problem, right? There may be efficient ways of doing it. If the current methods are not suitable enough, there may be efficient ways of doing it, and we can look at it separately. But to your question of should we put it in the same section, I wouldn't. Because, why? Because, over time, as we have implemented this section in the linker, it is best to not put too many different items in a section, because linker then has a harder time. SFrame sections are merged in the linker, which means that the linker really has to see what is being done, actually know exactly what is the data in that section and merge. So just for that aspect, and it's not something that can be ignored actually, so you should always try to put different entities in different sections. Now, whether you want to handle this as, SFrame symbol information wouldn't be the right thing to do either, because symbol information is again something that many entities need the same purpose, right? So I don't know if your question was more on the aspect that you want that to be more optimized.
No, the goal was typically not to have to parse the dwarf symbolic information, which is a complete nightmare to do.
Yeah. So like we're trying to keep it as simple as possible. That's why the SFrame is simple. So we're working the kernel side. It's trying to provide stuff that makes user space easier. I mean, the tracing side, I'm having information to try to say, here's a file, here's the offset into the file. Like in ftrace, I'm working it so when you see a stack trace on ftrace, you'll see each of the addresses. Actually, it won't show the address in memory. Actually, it will show the address in the file, and then maybe even a hash to tell you how to find that file. And then you can just look at, there it is, and ObjDump will even tell you exactly where it is. So you don't even need to use all of Dwarf.
So this information has to be available when you are getting the stack trace. So you want it to always be there. With the IP that you get from this, then later on, you can get information like the build ID that gets in the metadata, let's say for perf or for something else, or the file name. And then you do a query to a debugging for the server, get the extra information for line numbers, if that's just what you want to get just for this. And then you get the symbol from the symbol table and the source file and file number and line number.
I have a question about user space stack tracing in the kernel. What does it mean exactly? Is it for when I'm using perf, or is it replacing a stack tracer that already exists?
Sorry, I missed bits and pieces of your question.
Okay.
I'm the one doing the work, so.
Yeah.
All right. Can you repeat my question?
So basically, your repeat of the question is like, basically, is it going to replace like what's going on right now? Actually, no. It's actually going to be using the same thing. The only differences that we had to do was, as Indu said before, to read the SFrame information from the kernel, it's in user space, so we have to page fault. Unfortunately, like perf will set off NMIs, and then we have to read that. You can't read user space and page fault things from NMI context. So we're working on a deferred infrastructure right now that will delay the user space stack trace. So what's happening is when you do a kernel stack, you do a kernel stack trace, and then you request the deferred stack trace, and you get a cookie. And that cookie actually goes into the ring buffer into perf. And then when we go back to user space, then perf will record the cookie and the stack trace. So then the user space side of perf goes back to all the kernel stack traces that had that same cookie and appends the stack trace. So you still get the same information. It's still going to be, everything's going to look identical. It's just that instead of recording the user space stack trace at every single time you do that, you get a cookie each time, and you only do it once for the user space stack trace. Did that answer your question?
Yeah, I have a question about the ARM 64 kernel traces. So as far as I know, or for the live patching, so as far as I know, it currently relies on ORC, and at least on x86 and maybe on ARM as well. So do you need SFrames in the kernel for live patching, because ORC
is x86 only.
Yeah.
Okay.
Well, actually, what happened was ORC is x86 only. It's specific for x86. Josh, took everything from that. And the point is, what happened was, since Indu's working on getting SFrame on all architectures, the ARM folks were like, hey, because they've been wanting to try to get ORC, but they couldn't figure out how to do it. But now, we get it for free by just compiling the kernel with SFrame support. Now we have SFrames. That's why it may actually, on x86, might replace ORC. So, I mean, it's already in the compiler.
So, thank you.